sequence number was x and the length was b, then your ACK would be for x plus b. Your next data packet, the sequence number would be x plus b. And again, if the length was b, then your ACK would be x plus 2b. The packet after that would start at x plus 2b, and the ACK would be, again, x plus 3b, and so on. Okay? So the sequence number of your next packet is the same as what the next expected byte that your previous acknowledgement gave you. In this, I'm assuming no packet loss, of course. Does this make sense? Yeah? Okay. So going back to our TCP header, we've now filled in the sequence number. This is the offset of the first byte. We've filled in the acknowledgement, which is the next expected byte. Okay? So the first byte, first unacknowledged byte, such that all previous bytes were acknowledged. And then finally, for reliability, we also have a checksum. And the checksum in TCP is over the data, as well as actually a few fields from the IP header, but we're not going to get into that in detail. Okay, so we need checksums for reliability. We covered that in a previous lecture. Moving on, any questions on reliability in TCP? Okay. So flow control, we have the advertised window, as promised. And the way we're going to use it is that the sender maintains a window. The left edge of this window is the first unacknowledged byte. You've seen this figure before. The right edge, if we ignore congestion control, you cannot go further than the advertised window. That was what we said was flow control. So what's left in this header? We have a header length field. Just like in IP, this is in units of 4 bytes. It covers the length of the header. What about the length of the data? It's a bit of a trick question. The length of the data you actually get from the IP header gave you the length of the entire IP packet. So you take that length and you subtract out the TCP header length, and that gives you how many TCP bytes, data bytes are in the TCP payload. Ignore 0. There's something called an urgent pointer, which I'm just going to mention it here, but we don't worry about it in this class. The urgent pointer, the idea here when they designed it was, let's say you'd sent a bunch of data to a receiver, that it was processing that data. And then you have, the equivalent of a control CO. You want to stop processing. It's important that the receiving end stop taking in the data and processing it. You will have the ability to then send some data with this urgent byte flag, or the urgent flag set and the urgent pointer saying, here's this data is urgent, you need to pass it up to the application immediately. And it would bypass any bytes that had arrived before it, and it would not necessarily wait for all the bytes to be received. As far as I know, not used very widely, but that was the original reason for having it. We have some options that, again, we are not going to go into those either, but there's a set of options to specify additional things. One that, as an example, we've talked about selective acknowledgements as something that approximates full information acknowledgements. That was added to TCP later as an option. So TCP options are there to allow evolution of the protocol. But again, we're not going to talk about them in this class. So that leaves us with these flags, and I'll get to that just in a minute when we talk about the connection setup and teardown. So next one on our list was congestion control, right? We're not going to talk about that today. There's one question for you, though, is the congestion window, there's no place for it in the header. Did we need it? Why do we not have a congestion window in the header? Yeah, the congestion window is the sender figuring out at what rate it should send traffic into the network. Right? The receiver doesn't need to know it. It's irrelevant to the receiver. And the receiver doesn't have input into that congestion window calculation. So congestion window is just this algorithm run at the sender. We don't need to communicate it between sender and receiver. So it has no place in the TCP header. So the last one is connection establishment and sequence numbers. So let's start with this at a fairly high level, and then we'll actually look at what headers look like as you're setting up connections. This, again, is sometimes confusing to people because there's a fair amount of detail in what's happening. So the high-level TCP connection establishment follows what we call a three-way handshake. Okay? And it's used to initialize state at both ends, but also to exchange initial sequence numbers between A and B. So the way this looks at a high level is it starts, and this is why it's called a three-way handshake. There are 3 steps. The first step is host A is going to tell B, I would like to open a TCP connection. It does this by sending a SYN message. This is a synchronized to set up a TCP connection. Okay? So we call this a SYN packet. B responds, if assuming B is okay setting up a connection, B responds with what we call a SYN ACK. Right? And the reason it's both is it's doing 2 things. It is one, acknowledging, B is acknowledging that it received A's request for a connection. That's the ACK part of it. But B is also sending its own SYN message, because remember we said TCP is bidirectional. Okay? So the first SYN going from A to B, A is telling B, I would like to send you data, and here's my initial sequence number. The SYN ACK, B is telling A, got it, you can send me data, and here's my initial sequence number because I would like to be able to send you data as well. Okay? So it's both a SYN and an acknowledgement. And then finally, A will acknowledge B's initial sequence number saying, I got your initial sequence number, I'm ready to receive data from you as well. Okay, so this is where we see the full duplex nature. Any questions on the high level setup? We'll then step through headers and how this gets done. Okay, so it's a handshake. They've agreed to set up a connection. Each side has told the other side what initial sequence number it wants to use. And each side has also acknowledged to the other side that they've received the initial sequence number from the other endpoint. And then once you have this three-way handshake is set up, you can start sending data. So let's look at that in terms of the TCP header. And now we're going to expand this field here that we had called flags. And so ignore the bottom 4 for now. Just focus on, there are 2 flags, so they're 1 bit each. One is a SYN flag and the other one is an ACK flag. When you set it to 1, it tells you that this packet is either a SYN packet or an ACK packet or both. Okay. So let's start with the first step in that three-way handshake. And first, let's get a few things out of the way. So what is in this header? We have A's port and B's port. Right? We know what those are. We have no options, and so the header length is just 20 bytes. And now let's focus on, this is the first packet in that handshake. So it's a SYN packet going from A to B. So the source is A's port, destination is B's port. The SYN flag is set. All of the other flags are not set, right? Because it's not an acknowledgement message, and ignore the other 4. And now look at what these fields are. The field here for sequence number is A's initial sequence number. Okay? So this is how A and B are going to synchronize on the sequence numbers that A is going to send to B. The acknowledgement field here is not relevant because we've not set the acknowledgement bit. Is this okay? Yeah. No. So there's no payload because you're not sending data yet. Okay, I'm on step 2 now. So now we're at the stage where B has received the SYN, and remember, it's sending back what we call a SYN ACK, right? So let's step through this. It's coming from B, so the source is B's port, the destination is A's port. Importantly, we are now setting 2 bits in the flag. So it says that it's both a SYN message and an ACK message. Okay. The sequence number is now B's initial sequence number. Okay. This is how B is going to start numbering its byte stream. And at the same time, it is acknowledging A's initial sequence number +1. The +1 because we're doing next expected byte. This is also why when A starts sending data, the very first byte in A's byte stream is going to be initial sequence number +1. Anyone want me to repeat this, or is it clear? Yeah. So at this point, B has told A that it accepts and it's ready to hear the next byte. And and so on receiving this packet, A now knows that it's good to start receiving. It can start sending data because B knows what the byte stream numbering should look like. And so the last step in this three-way handshake is A is now acknowledging the SYN ACK. So this is kind of A's way of telling B, I heard your initial sequence number, you can start sending me data. And so what this looks like now, we have only the ACK bit set. Right? There's no SYN here. We're not exchanging initial sequence numbers anymore. And so this is coming from A, so A is port, source port, B is the destination port. The sequence number doesn't matter because it's only an ACK, and the number that A is acknowledging is B's initial sequence number plus 1. Yeah? Are we good? Oh. Good question. I believe you would get it here from on the ACKs. Well, is it set on the SYN ACK? Let me get back to you on that one. I don't know. I know when you start sending data and you're ACKing data bytes, your advertised window would be a valid field there. I actually don't know whether you set the advertised window as part of the handshake. Do any of you know? No. Okay, we'll get back to you on that. Okay? Any other questions? Okay, so last bit is we're going to now talk about tearing down that connection. So we've set up all this state. You do need at some point to delete the state when your transfer is done, or for whatever reason you want to tear down the connection. Okay, so this is where the last two flags that we are going to consider come into play, the fin, which is the finish, and the reset flag. Okay, and the way this works is actually pretty straightforward, though it's been exploited by security attacks so many times that it took a few iterations to get it completely right. So in your connection here, we've done the three-way handshake. We've sent data, we've gotten ACKs, and now let's say that A is done. It's finished sending all of its data. Okay. So what it's going to do is it's going to send a finish. This is kind of a graceful termination, or what we call normal termination. So A is going to send a fin, which is a finish message to B. B is going to acknowledge that fin. So it's going to say, I get it, you're done, you have no more data to send me. At this point, we say that the TCP connection is half closed. Okay? We understand that A has no more data to send B. We don't know anything about whether B was done, which is why it's half closed. You cannot delete your state at this point. Okay? So A cannot just tear down the TCP connection and say, I'm done. Okay, so instead, A is going to wait. At some point, B is going to send a fin message to A. This is now B telling A, I'm done sending you whatever data I wanted. At which point, A will acknowledge that it received the fin, and then it waits for some timeout period and then deletes all of the connection state. Okay, so this is one normal termination where each side is taking turns to tear down or close the connection whenever it's done sending data. There are more complicated variants where both sides can be sending fins at the same time. We're not going to get into that. Yeah? Oh, yeah, either side. Sorry, I should have said this. Either side can send a fin whenever it's done. But it would play out in reverse then. Yes, so let's walk through that. So if B sent a fin to A, what is that telling us? That is telling us that B has no more data to send A. But B is still expected to be up and acknowledge any data that A sends it. And only when A is done sending, which is why we say the connection is half closed, because A's side is still open. And it doesn't matter which side is done first. Does that make sense? Okay, so then the other type of termination that's relevant is what we call an abrupt termination, or you've probably heard of your TCP connection being reset. That's where this comes in. This is really when a pretty drastic form of terminating a TCP connection, either side can just send a reset message to the other side. And when you send a reset message, that's it. So typically the example here people give, oh, actually, let me get to that in a minute. So the behavior is just either side can send a reset. You don't have to acknowledge the reset. If the reset is not delivered reliably, that's fine. Any data in flight, there is no guarantee that it gets delivered. If the other side continues to send data, you can continue to send resets back to it. Why would this seem useful? There was the intended use and then there's the current use, but let's first talk about the intended use. The intended use, is typically, imagine that A had rebooted or restarted, or your process crashed and you reset. So when A reboots and comes up, it no longer has that connection state. But B doesn't know this, and so B is sending data to A. So sometimes A receives